Let's get started. Chapter 5. Okay, chapter 5. We're going to study carboxylic acids and a derivative of a carboxylic acid called esters. Okay, so our main focus are two types of compounds. And both carboxylic acid and esters are still organic compounds containing only three elements: carbon, hydrogen, and oxygen. Okay, oxygen. We're not studying any new elements yet until chapter 6. Okay, chapter 6. Okay, first, the functional group of carboxylic acid is something we have seen already in chapter 4. The functional group of carboxylic acid is carbonyl group with a hydroxy group on the same carbon. So you can call it COOH. Okay, COOH. Of course, the other group will be a carbon group. But this is the functional group with a CO double bond. We know that's called a carbonyl group. And on the carbonyl group, there's a what? Hydroxyl group. Okay, COOH. And a lot of times, we abbreviate COOH into this format, COOH. That one is less commonly seen, actually. This one and that one are very commonly seen, especially this COH. But you need to know these two O's are not bonded together. Those two O's are both bonded to what? To the carbon. One is double bond. One is what? Single bond. Okay, you know what these two O's are mean. They're not continuous like two O bonded together like shown this. This is just an abbreviation of the carboxyl group. Okay, carboxyl group. And then, like we said, you have seen the functional group of carboxylic acid in chapter 4 already. Where have we seen it? In the oxidation of what? Aldehyde. Okay, in the oxidation of aldehyde. We have seen that. We have those in the test as well. When an aldehyde is oxidized, okay, for example, by Toland's or Benedict's reagent, the aldehyde CH will be converted to what? COH. Like I told you during the practice, what you need to do is simply insert an O between the C and what? The H. That's how you get what? COH. And this is a carboxylic acid. Okay, carboxylic acid. And of course, ketone. Because the C does not have a hydrogen attached to, so ketone cannot be further oxidized. Okay, ketone cannot be. Oh, sorry, this is an aldehyde. It's not ketone. Still an aldehyde. This is a real example. Okay, so this reaction also tells us a carboxylic acid can be synthesized from an alcohol. Okay, to be more specific, from a primary alcohol. Okay, from primary alcohol. A primary alcohol after oxidation will give you an aldehyde, which can be easily further oxidized into what? Into a carboxylic acid. Okay, this is how we can make a carboxylic acid from a primary alcohol. And most cases, the reaction won't even stop at the aldehyde stage. If you use a strong oxidizing agent, if you oxidize in primary alcohol, what you will get is just carboxylic acid. It's actually harder to stop at the aldehyde stage unless you have a selective reagent that can stop at the aldehyde. Okay, because aldehyde is actually easier than the alcohol to be oxidized. So once you get aldehyde, it's just further automatically being oxidized into what? A carboxylic acid. All right, so that's how, if we want, can prepare a carboxylic acid. Next, naming. Okay, naming. Because COOH, take a look at the functional group. This carbonyl group is bonded to a carbon and what? An OH. That means this carbon is always at the end. Why? Because it's bonded to what? To an oxygen now. There's no more carbon here anymore. only carbon on the other side. So that means the carboxyl group will always be number 1 because it's at the end. And because of that, you guys have experience on naming already. If the carbon is always number 1, no exception, no surprise, then we do not need to what? Number it in the name. We do not put a number in the name. Okay, this is always number 1. Okay, and other than that, the naming is very straightforward. Okay, the name of a carboxylic acid is simply replacing the E of alkane, the last E of alkane, with OIC acid. With OIC acid. OIC acid, between OIC and acid, there's a space. Okay, there's a space. So for example, this molecule, the number of chain is 1, 2, 3, 4, 5. The alkane name is what? Pentane. You drop the E of the pentane, replace it with oic acid. So the name of the acid is pentanoic acid. Okay, there's no 1 in front of it. Why? Because this carbon is what? Always number 1. You don't have to number that one. Okay, pentanoic acid. And give you a minute or two, take a look if you understand the name of the middle molecule and the molecule on the right. One, two, three, 3 bromo. 1, 2, 3, 4, 4 methyl. You guys see that? Okay, there's no number in front of the last name of the molecule because again, a carboxyl group is always what? Number 1. Always at the end. Okay, always at the end. Next, if a carboxyl group is attached to a benzene ring, then this whole system, this whole structure gets a new pair name. This pair name, you guys have seen this already in chapter 2. It's called benzoic acid. Right? You guys remember that in chapter 2? Okay, we have seen that if a carboxyl group COOH is attached to benzene ring, this whole thing in purple is is named as what? Benzoic acid. And because this is a new pair name, the carbon attached to the carboxyl group on the benzene ring is what carbon? Number 1 carbon. Okay, number 1 carbon. So here you can see that 1, 2, 3, 4. 4 chlorobenzoic acid. Or we can call it p-chlorobenzoic acid. P stands for what? 1, 4. Okay, pair of 4. And this is 3, 1, 2, 3, 4, 5. So 3, 5 dichlorobenzoic acid. You guys see that? Okay, again, the whole thing covered in purple or pink is what? Is a pair name, benzoic acid. So if you call it benzoic acid, you name this whole 7 carbons already. All you need to name is what? Whatever not in the pair name. The groups. Okay, the groups are on the benzene ring. So the carbon attached to the carboxyl group is number 1. Okay, it's number 1. So that's all. Naming, easy? Good? Any questions I can explain? For naming of carboxylic acid, I said, we spent a lot of naming in the first 2 chapters. Then after that, the system is the same. Only thing you need to know is, what is the suffix for benzoic acid? Is what? Replacing the E of alkane with OIC space acid. Okay, OIC space acid. Next, some physical properties of carboxylic acids. Okay, the first physical property, okay, is the odor. Okay, is the odor. Okay, you guys smelled or tried the odor of aldehyde ketones. They're what? They're very pleasant, right? A lot of aldehyde ketones have pleasant odors. Okay, so carboxylic acid also have their odors. Okay, their odors are normally sharp and generally assuming as unpleasant. Okay, it depends. Somebody like it. This is not a really 100% unpleasant odor. I mean, there are some odors like thyle. We talk about the skunk odor. Nobody will like it. Okay, I don't think anybody. But this one, it's sharp. Okay, it's sharp, but generally speaking, unpleasant because it's sharp. It's kind of irritating, especially if you're spelling pure ones. Okay, if you're spelling diluted ones, it may not be as unpleasant as you think. Okay, now, how sharp, how unpleasant? If you buy a bottle of vinegar, if you breathe it really hard on the bottom of vinegar, if you can tolerate that, that means you don't think it's unpleasant. If you think it's too sharp, unpleasant, then it's unpleasant. Vinegar is only 5% of a carboxylic acid. With the 2 carbon, we call acetic acid. Okay, 5%. The one you buy from grocery is normally 5%. 5% means what? Is 90% is water. So if you can see that is pleasant to think about, is stronger, then can you tolerate this? So normally people call it unpleasant odors. But that's the odor typical for carboxylic acid. They're similar. Okay, again, vinegar is a 5% solution of acetic acid, 2 carbons. Okay, with 2 carbons. Oh, by the way, this is acetic acid we have here. This one, here, you see that? This is what's in vinegar, 2%, 5% of it. Here, this is 2 carbon acetic. Acetic acid, by the way, is not a IUPAC name, it's a common name. Okay, we use this common name more than the IUPAC name should be ethanoic acid. Okay, because it's ethane replaced with what? ONE followed by acid. So the IUPAC name is ethanoic acid. Okay, not acidic, but nobody called it ethanoic acid for this one. All right, so that's for odor. Next, because of the functional group COOH, okay, very unique functional group. Carboxylic acids, they form a strong bonded structure like this. We call it a dimer. Okay, call it a dimer. You can see that in this picture, there are 2 carboxylic acids, COOH, COOH. What happened in this dimer is the O on the CO double bond of carboxylic acid 1 is now interacting with what? The H of another carboxylic acid, or carboxylic acid number 2, if you want. And then the O of the carboxylic acid number 2 is interacting with what? The H of carboxylic acid what? Number 1. So they're like bonding like, if you imagine this is O, that's H. They're bonding like this. That's what we call dimer. They're 2 molecules. And because, of course, the dashed line is something we have seen before called hydrogen bonding. And because of these 2 hydrogen bonding, like 2 crabs biting, they're fighting together, tight. And because of that, imagine if you have 2 crabs with both of their claws biting with each other, it's very hard to what? To pull them apart. Maybe you will break their legs before you separate these 2 crabs. The same thing here. Because of the dimer structure, okay, 2 hydrogen bondings, the interactions of carboxylic acids molecule themselves are very strong. Okay, the molecules can be very hard to separate. That means what? If you want to change from liquid to gas state, you need what? Very high temperature. You need a lot of heat to separate it. So that tells us carboxylic acids have very high boiling points. You can see I put it here. The highest of any type of organic compounds yet study, consider.
So more than alcohols?
Yes, much higher than alcohols. Okay, much higher than alcohols. Does it make sense, guys? Because of the dimer structure. Here, okay, you can see that our chart becomes better and better, like more and more complete. This line is alkanes and ethers. This line, aldehyde and ketones. This line, alcohols. This line, carboxylic acids. Carboxylic acids, their boiling point are even higher than what? Than alcohols. And also, yes?
So is this same thing like for the alcohols, aldehydes, all that? Is it more carbons the higher?
The same, yes. If you're talking about carboxylic acid themselves, you can see that the boiling point also increases as the number of carbon increases. Okay, that trend is the same for all types of organic molecules. That's why, like we said, always say, if you want to compare molecules of different types, you have to put them into what? Similar in size. Okay, you cannot compare like a 1 carbon carboxylic acid with 5 carbon alkanes. This is not comparable because they have different sizes. Okay, sizes. So that's why here in the next table, okay, so this one gets more and more complete too. You can see that those 5 molecules, okay, those 5 molecules represent one from each type: alkane, ether, aldehyde, alcohol, and carboxylic acid. Okay, that why in this table we choose those 5. You can see that the molecular weight that is assigned to quantify their sizes. Okay, you can see their molecular weight are what? Very similar. So that means we can compare these 5 because they're from different categories, different types. And you can see their boiling point. Okay, of course the number doesn't matter much, but take a look at the changes, the differences. Alkane and ethers are what? Very similar, the same. Aldehyde, higher. Alcohol, higher. And carboxylic acid is what? The highest so far. Okay, this table shows you that. Okay, it shows you the comparison between different patterns. But again, you have to compare molecules of what? Similar sizes. Okay, similar molecular weight. Okay, we don't study this concept in 102, but molecular weight is some numbers to quantify the size of the molecule. Correct? That's boiling point. Okay, next, because of the carboxyl group, you can see that very obviously the carboxyl group has the oxygen, has the hydrogen. Both parts of the molecule, both parts of the carboxyl group can interact with what? With water. Okay, the oxygen can interact with the hydrogen of water. The hydrogen can interact with the oxygen of water. So this group is very easy to interact with water molecules, making carboxylic acids very soluble. Okay, very soluble. Okay, very soluble.
So the solubility is higher than alcohol?
Alcohols, yes, because the functional group is more interacting with water. Okay, this chart also shows you the trend of solubility with the similar trend that we have seen many times before in chapter 3 and 4. We know carboxylic acids are extremely water soluble. You can see that from carbon number 1 through carbon number 4. The solubility is what? Called complete. Means what? You can mix with any ratio of the acid with water. They will dissolve. You can work 99% of the acid, 1% water, still going to dissolve. But the solubility does decrease as the number of carbon what? Increases, gets higher. Okay, you can see that increase to 5 carbons, the solubility does drop to what? 5 grams per 100 mL of water. If you increase to 6 carbons, further decrease until 7 and maybe 8 carbons, the solubility of the carboxylic acid is close to what?
0.
To 0. Why? The same thing, because the R group
Gets bigger.
gets bigger and what? bigger. That means the R group gets what? More and more dominant in this resulting molecule. And the R group usually is what? Hydrocarbon chain, which doesn't like water. Okay, doesn't. The one that makes carboxylic acid water soluble is what? Is this part. Nothing to do with this part. So if this part gets bigger, the solubility is going to what? More and more like this part. And again, this part is hydrophobic. Okay, so that's all we need to know about physical properties. Good? 3 things. The odor, sharp, unpleasant. Like vinegar, only stronger. Number 2, because the dimer structure, the carboxylic acid boiling point is what? Very high. The highest we have studied so far. Okay, again, you have a chart before. Okay, just use those. Okay, use those. Okay, you can see my slides. I don't like putting words there. I know you don't like reading. These are very vividly help you to understand these trends. Okay, you can use your own language to interpret it. What is this? Right? These dots are carbons. Okay, as you increase the number of carbon, the solubility is going to what? Decrease. You use your own language to interpret this. It's better than I put something in here. I don't want to read too when I teach you. I don't know what I don't have time to go turn back and read. So the picture is the best thing to help you to understand. And you can pick your own notes with your own language. Okay. Next, reactions. Okay, reactions. Oops. Carboxylic acids. Okay, their name has the word what? Acid. Okay, so of course they are acids. They're weak acids. Okay, most organic acids are weak acids. Now, because of the acids, they can do something with water. That's the reaction you have even seen in your test. You guys remember that? It's the same reaction in what? Phenol. Is that right? We said phenol is a weak acid. You guys want me to turn back to phenol? Okay, I can turn back. Okay, some of you forgot about that reaction. Okay, let's turn back to chapter 3. Chapter 3. Here we go. Some of you forgot, but I hope this reaction can remind you. And that reaction is also in your test, by the way. Okay, this is the reaction we have studied in chapter 3. Phenol. We called phenol a weak acid. Take a look. Why we call it weak acid? Because the OH of phenol can break, and the breaking is not homogeneously, it's heterogeneously. So the hydrogen is actually coming off as a what? Hydrogen plus. Is that right? We call hydrogen plus a proton. And hydrogen plus is accepted by what? By water. That's why water becomes what? H3O plus. Do you guys recall that now? And of course, when hydrogen is off as a hydrogen plus, the O will be what? O negative. That's why we call phenol an acid, because phenol can give this guy hydrogen plus. This is hydrogen plus. It's just now combined with what? With water. Do you guys recall that now? You have the same thing. If you put this thing in your test, you get 5 or 6. I forgot. This is exact the same thing from the notes. All right. Next. Now, if you understand that, let's change back to carboxylic acid. The same thing happened. In carboxylic acid, the COOH, in particular the H, will give a hydrogen plus to water. You guys see that? Water becomes what? H3O plus. And then the O becomes what? O negative. Do you guys see that? COOH now becomes what? COO negative. Okay, the OH bond breaks unevenly. The oxygen took all the electrons. That's why hydrogen is hydrogen plus. Okay, this is what happened. And of course, hydrogen plus doesn't exist alone. Hydrogen plus is always taken by water. accepted by water. That's why water becomes what? H3O plus. Okay, the bottom reaction, just show you another example. You won't see that in your scope. Is a molecule with 2 carboxyl groups. Okay, that means this molecule can give what? 2 hydrogen pluses. Okay, that means you need 2 water to take them. Okay, this one is called oxalic acid. Okay, oxalic acid. Does it make sense, the reaction, guys? You will see that in your quiz. I remember that. This reaction, again, demonstrate what? Carboxylic acids are what? Acids. Why they're acids? Because they can generate what? Hydrogen plus in what? In water. That's the definition of acid. That's one of the theory of an acid. What is an acid? Acid is a species when dissolved in water can generate what? H3O plus. Does it make sense? Okay, now, in this chapter, I'm going to spend a few more words on the word weak. Okay, what is a weak acid? Okay, most organic acids are weak acid, including phenol. We didn't talk about much in phenol. Okay, the reason I want to save it here. Weak acid means the carboxylic acid here, like this guy, when they donate the hydrogen plus to water, not all the molecule does this. Only a small percentage of the carboxylic acid that is dissolved in water does this reaction. The majority of the molecule is still COOH. In another word, if you have a bottle of vinegar, for example, this is vinegar acid. Most of the acetic acid remains this guy, intact. Only a small percent of the vinegar acetic acid becomes what? Becomes COO minus. If it becomes CO, that means what? Hydrogen is off. But that only happens in a small fraction, small percent. How much percent? We have a table next page to show you the percentage. Okay, acetic acid, here, only what percent? 1.3%. That means what? 98% of the molecule is still the COH. Only a small percent ionized. Okay, ionized. You can see that these are the percentage of different acid. Okay, these are all common names. Carbon number 1 to all the way to carbon number 6. Again, these are all common names. Okay, you can see their percentage is only less than 5%. Telling us what? They are weak acid. That's what the weak comes from. Okay, comes from. Okay, again, percent tells us what? If you have 1,000 molecules, for example, imagine if you have 1,000 molecules. Only 1.3 of them does that reaction. The rest, the 990, 80 something is still what? They're doing good. Only 1.3 molecules what? Gives off the hydrogen plus to become O minus. Right? Next, because they're acids, okay, because of the acids, they can react with a base. Okay, with a base to give you water and salt. Okay, let me point out this reaction for you, something we have studied also in chapter 3. When we look at an acid, I told you what do we do? We have an acid, actually this way we now know this is an acid. So what would you do for its reaction with base? You use your pencil to what?
Put negative in.
Mark the charge, is that right? Put the negative charge on the what? On the O, put the positive charge on the H. Again, very gently use your pencil to mark it. And then NaOH, you do the same thing. This way you can mark it even harder. Because NaOH are actually made by charged ions. Sodium is plus. OH is what? Negative. Very good. So when they react, the real species that are in the reaction are actually the H, again is what? H plus reacting with the OH negative to give you water. They're the ones that are reacting. But when H reacts as H plus, O becomes what? Take a look. O negative, Na becomes Na positive. You just put them together. They're not reacting. They're just remaining. Does it make sense, guys? Okay, mark the charge. Minus, plus, plus, minus. The species that are reacting again are what? H plus and what? OH negative. Does it make sense? And then they become water. Okay, what's remaining are the O minus here, Na what? Plus here. Again, you copy whatever the R is. Okay, with that, guys, complete the bottom two reactions. I'll give you 3 minutes. Complete the bottom two reactions. Perfect. Glad I put that one there. Sometimes on student notes, I gave the answer already. I didn't know. I still asked it to. It's not recognizing. It's the same answer. Very good. Yeah, great. It's clicking now. It's good. It's not late at all. She forgot to bring homework. Oh. Anyone? I can check. Beautiful. Perfect. Beautiful. Yes, great. Perfect. Now see, you have to copy this first. You're missing something, even you did something correct. If you're missing that, it's still wrong because correct. Correct. And also O becomes O minus. Hydrogen is gone. Hydrogen is gone. Correct.
This chapter is short.
Not long. You see, I thought it was O minus followed by Na what? Plus. You see that? It's long. So O minus followed by K plus.
Which one is it?
And the same O minus followed by Na plus. Correct. Take a look at the top. Always take a look at the top.
Drew it out and then
The
I
bottom
put it
part.
and then had an outline name. Sorry.
I think I have the answer here again. Eric, here is the answer. Make sense? All good? Hope you all can do it right in the quiz and test.
Just drop that hydrogen and then add.
Hydrogen reacts with the OH already. They become water already. You don't even need to put the water because they're in water. The whole thing is dissolving water. So you basically from the reaction they generate one water molecule. You can put it there. You don't have to. What is the change of the organic compound is what we care for most organic reactions. Is the carboxylic acid OH becomes what? O minus what? whatever the metal plus is, K plus or sodium plus. We call the product a salt. Okay, salt. Good? Okay, now, before we even move on, we can have a few words about these guys called the salt of carboxylic acids. Okay, carboxylic acids. This is a very, very common practice done in pharmaceutical industry. Okay, a lot of clinically used drugs, medicine, are actually carboxylic acids. Okay, carboxylic acids. And then by common practice, these acids are always turning to their salts when used as a medicine. You may wonder why they do that. Why they use this reaction to turn an acid, COH, to a salt. The reason is very simple. To increase the solubility. Okay, increase the solubility. We know carboxylic acids, guys, one thing we just studied, the solubility is going to what? Decrease as you increase what?
Carbon.
The number of carbons. Most drugs, their number of carbons are not even small. They're never, rarely you see like a few carbons. So even the drugs are carboxylic acids. Most likely they won't be dissolving water. Think about it. If something doesn't dissolve in water, first you cannot what? Use it as an IV medicine. You don't even dissolve. So common practice is to change the COOH into what? Into the salt. This acid, I use an extreme like a case. This acid has how many carbons? Take a look. 18 carbons. This is called a fatty acid, in fact. Okay, we'll study that in chapter 8. What is a fatty acid? Too fat. They don't dissolve in water. They're like a fat. What does fat does? Fat doesn't dissolve in water, right? You put fat in water, it will float. That's why we call these fatty acids. They're from fat and oil. But if I convert that acid into a salt, this thing is still fat, but it dissolves now. That's why a lot of pharmaceutical industry, they are doing this type of reaction. Okay, one example I'm showing here. Okay, this is the structure of penicillin G. Okay, very commonly used antibiotic. Okay, you can use orally, but you can also use IV. Okay, take a look at the carboxyl group. COO what? Minus Na plus. Okay, if you guys later on, I think nowadays people make it in solution already. When I was little, okay, you actually can see a bottle of a powder of penicillin G, and the nurse will mix it with saline and mix it. Okay, when I was little, my mom was a nurse. Okay, they can mix it and shake it very well, then use an IV or muscle injection. Okay, the reason they can make it soluble, take a look how big the molecule is. It's not water soluble. But if you change to a salt, penicillin will be water soluble.
They still do it. We went to Saudi Arabia.
Okay, yeah, some countries they still supply as powder because it's stored longer time. Nowadays, if you hear, I think mostly is in just made in solution already. But in solution, they're in what? In the salt. You can call it, sometimes even read the label, called a sodium something. That means that's what? It's salt already. Okay, sodium, salt. So again, the thing is, I want to show you an example. Carboxylic acid salts are a common practice to make carboxylic acid molecules what? Soluble. Because all salts are very water soluble. Okay, no matter how big the molecule is regardless the size of the molecule. Okay, because of the charge. The reason is because now we converted something into real charge. Okay, besides that, these two carboxylic acid salts from benzoic acid, okay, benzoic acid, this is sodium benzoate, this is potassium benzoate, they're the same. Okay, those are, you can see that they're salted from what? Benzoic acid, right? Okay, you can see benzoic acid. Those two salts are very commonly used as a food preservative in all kinds of preserved food, especially ketchups. or if you buy those like a chili pepper paste or whatever paste, you read the label, most likely they have this guy. For example, this is the label of maybe a ketchup, I don't know. It says sodium benzoate on it. You can read it. If it is a ketchup or something paste, most likely they need to add some preservative to kill bacteria. Otherwise they will go bad fast. And those are very commonly used as antibacterial food preservatives. Okay, you eat them every day. I don't know if you can research, are they really good for health or not? Most likely not, but they're FDA approved and commonly used, extremely commonly used. All right, good? That's the first part of the chapter. We'll move on. Okay, we'll finish as much as possible. But that's the first chapter about carboxylic acid. We studied what? Naming. We studied physical properties. We studied two reactions. The first reaction is what? Is why they're acids. Because they can change or they can donate a hydrogen plus to what? To water. Right? To water to give you what? As H3O plus. That's why they're defined as acids. And because of the acid, they can react with what? With a base to be converted to a what? To a salt. And again, converting to a salt are very common practice in pharmaceutical industry. In the future, when you're a nurse, if you read something, sodium something, potassium something, they're salts. That means you know, oh, they're carboxylic acids. Okay, the name contains the sodium or potassium either. Right? So that's carboxylic acid. Right? Two reactions. Next, we're going to study the derivative of a derivative of a carboxylic acid that is formed by reacting a carboxylic acid and an alcohol. Okay, and an alcohol. These two reacting together. Okay, this reaction here shows you two structures. The left, COOH, is a what? A carboxylic acid. Is that right, guys? On the right, ROH is what? Alcohol. You guys see that? The R and R, just any groups. They can be the same, they can be different. I put a prime here only to what? To distinguish this is from the carboxylic acid, this is from the alcohol. They can be the same. We good? Okay, take a look what happened. When these two types of molecules react, okay, these two types of molecules react, you remove a OH from the acid, COOH. You remove the OH from the acid, you remove the H from the alcohol. You make a bond between the C and the O. You guys see that? Of course, you remove the OH, you need to put something back to it. Right? You remove the H, you need to put something back to the O. So these two now what? Bond together. So what do we have? COO what? R. Do you guys see that? Because they're bonded together. Do you guys see that? COO what? R. This is COO what? This is the new bond we just did here. The new bond. We call this bond an ester bond. Okay, this bond an ester bond. The resulting molecule is an ester. Okay, is an ester. Okay, we'll talk about this many times. If you look at the ester, this is the bond again. This side with the CO is from what? The carboxylic acid. Is that right? This side, the RO is from what? From the alcohol. There are two molecules joined together. But of course, if you want these two joined together, you have to take a what? Take away the water. The OH and what? The H. We call the reaction condensation because you need to take the water away. This also is called a condensation reaction. You can also understand, okay, you can also understand the structure of the ester. Okay, the structure of the ester as here. The OH of the acid, take a look, is actually replaced with what? With the OR. Do you guys see that? RCOOH becomes what? CO what? OR. So the OH of the carboxylic acid is actually replaced with an OR from what? From alcohol. If you do that, you're changing from a carboxylic acid to a what? To an ester. Very good. You can understand like that. But remember, this part is from an alcohol. RO is from an alcohol. Without the H, of course. Make sense? I created something extra for you guys. Okay, created something extra for you guys. How do we run this reaction? How do we make an ester? Take a look if it makes sense for you. If you have a carboxylic acid, you first what? Remove the OH. This is what you got. If you have an alcohol, you first what? Remove the H. This is what? What you got. Then what? Make a bond between the C and what? The O. You like this one? I mean, either one you like. You like this one or the previous one, they mean the same thing. And make it, just show you stepwise, how do you make an ester bond? Remove the OH from the carboxylic acid. You got this. Remove the H from the alcohol. You got what? That. Remember, you have two molecules. Then you have to join these two parts together because you took one thing from that, one thing from here. They're missing something. You have what? To make a bond. Remove the OH from the acid. Remove the H from the alcohol. Then what? Make the bond between what? O and the C. Is that right? You guys see that? Batteries are running out. Do you see that? Of course, you can write it better. RCO what? OR. You can just don't make it that long. Okay, put it in a nicer way. That's the what? The ester bond. Okay, ester bond. This bond is the what? Is the ester bond. The molecule, the resulting molecule is called an ester. Okay, an ester. Does it make sense? If it does, give me 1 second. I think your next page has answer already, right? Oh, where is it?
I already did it.
Oh, you did. You guys has it covered. Okay, that's good. So work on the next page. I'll come and check with you. Okay, I think my next page is not covered, so I'll cover it first. Right, I need to charge it. Give you guys 2 minutes. Work on the next page. The 2 examples. Make an ester, and let me take a look. Are these 2 the same as yours?
Yes.
Okay. You guys done naming that? Let me see it now. I can take a look. Yes or no, doesn't matter.
Okay.
As long as you give them those. Like I said, you should add water, but what we care most is the organic transformations. What are these two organic molecules becomes that. Then that's good enough for me. Very good. Very good. Okay, we'll all be coming. Perfect. Great. Again, guys, I hope you can do that in your quizzes, right? You're not done yet, right? No. What is the plus for? You need to make a bond between the C and O. Where's the bond? Between the C and O. See that?
Okay.
Not plus. You're just showing me two fragments, not a molecule. You need to make a bond. Bond. Connecting the C and the O. There we go. Even this long is not pretty, but that's good. That's correct. The same thing for the first one.
So it'd be this.
Yes, very good. Don't the one you show me are two fragments. You have to make a bond.
Okay.
You done?
Yeah, so I think just
Don't use R. Now this is not an R. Okay, look, this is what I think copy the structure.
and then here was
CH2 and then CH2. You see that? This is again copy first before you work on it. Yeah, that's correct. Yes. Yeah. Water? Yes or no, doesn't matter. You can add water, but you don't have to. But you know where these two that are removed went. They became what? Water. And something she's not sweet, you're missing. That's why I say copy first. There's an OH here. No, there. Yes. Don't miss that. Even you did it correct, but if you miss that OH, there's totally two different things in it. Okay, so like I said, you go to haircut, you don't lose not R or something. So that's the same. Don't lose anything other than that because the reaction only happened here. Right? Good? All right, let me take these two off. You guys can take a look, just make sure you got the same answer.
So we have to add, like at the end, do we need to add the H2O or
Yes,
do we have to
just
add
form a
that?
habit, just add it. But if you miss that in your test, I won't have your credits off.
Okay.
Let's put it this way. Okay, you're supposed to add water so you know where everything goes. Okay, you know the water came from what? It came from these two species. But again, in your test, if you miss a water, that is fine. You cannot miss this one. Okay. Make sense, guys? Nice? Okay, esters. Okay, esters are another group of organic molecules that possess very, very nice odors. As a matter of fact, those best smelling fruits, strawberry, pineapple, cherry, their odor, pleasant odor, are all because of the esters in them. Different types of esters. For example, here you can see that this ester you just made is the strawberry flavoring. Okay, this that they made is not from fruit, but from wintergreen. Okay, it's the odor of wintergreen. Okay, in one of your labs, you actually will make those esters, and you can smell it. Okay, we're gonna make in one of our labs, maybe next week or this week, I forgot. And we're gonna smell these odors. And then, as a fact, this next page I put it here. Okay, you can see that these are the structure of these esters, and these are the odors that These are esters are responsible for pear, orange, apricot, apple, pineapple, banana. You can see they're different. Now, okay, I know you don't care about the odor, but take a look at the structures of the esters. Okay, we said we're gonna do that a lot in the next class or today, depends on the time. If you look at an ester, okay, if you look at an ester, any structure of an ester, first, can you recognize now the ester bond? Which bond can you point it to is the ester bond?
CO single bond.
Which bond?
CO single
CO what?
single bond.
Oh, this CO single bond is what? It's the ester bond. Again, that's very important. You can make them, you can recognize it. This CO bond is the one you just what? Bonded. This is the ester bond. Here, ester bond. Here, ester bond. Here, ester bond. Ester bond. Ester bond. Ester bond. You guys see that? Again, you will use that a lot in the next few. Okay, you will do a lot of reactions based on this. So please, when I give you a structure of the ester, I know again you don't care the color. I don't care. I don't remember the color, the odor. But when I give you a structure of an ester, you know, hey, this is the ester bond. That's an ester. You guys see that? Next, after you find the ester bond, you can put your finger on it. Can you recognize it? Which part of the molecule is from the acid? Which part of the molecule is from the alcohol? Can you guys recognize it? Which part is from an acid? The one with what? The CO double bond is from what? From the acid. You guys see that? The one with the OR is from what? From the alcohol. You guys see that? Okay, any ester, you take a look, put your fingers on. You see that? Okay, keep that in mind. You will use this ability, this method a lot in the rest of the chapters. In the rest of the chapters. Good? Okay, this structure is drawing like this way. Of course, I can say anything on the left of my finger are from what? From the acid. Anything on the right of my finger is from what? From the alcohol. But the structure sometimes doesn't draw like that. All you need to know is after I identify the ester bond, the one with the CO double bond, the carbonyl, is from what? From the acid. The one with the OR is from what? From the alcohol. Okay, again, very important. You will use that in the next few minutes. Okay, next. There is a type of ester. Okay, type of ester that are formed by a diacid and a dialcohol. Okay, a diacid and a dialcohol. For example, like this guy. This acid has a benzene ring with 2 COOH on it. We call this a diacid. This alcohol has an OH here, has an OH here. That means what? 2 alcohols. We call this a diol. When they make an ester, okay, when they make an ester, they can join in a way to form a polymer. This is what happens. Take a look. We know the acid and the alcohol can make a what? Can make an ester bond, right? Take a look at the color. They're even color coded. Remove the OH from the acid. Remove the H from the alcohol. Bond the C and what? And the O. This is the ester bond we just did, right? That's just one reaction. But if you look at the molecule here, after they join together, on this side there's the what? Acid not reacted yet. Is that right? On this side there's the what? Alcohol not reacted yet. What does that tell you? It tells you this acid can react with another what? Alcohol. This alcohol can react with a what? Another acid, and you can go this on and on and on. So if you call this guy as A, that is B, you will end up with a long molecule of AB, 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 AB. Why? Because whatever you have an acid here, you have an alcohol. And if you have alcohol, you can get another acid. If you get acid, you get another alcohol. So you will end up with what? A poly. Okay, poly. Does it make sense? Okay, because you have two ends that are not reacted yet. Because they're what? They're both diacid and dialcohol. And we call the resulting molecule a polyester. Okay, a polyester.
Only
What?
one end will react
Yeah?
at one time.
Which one?
I'm saying like only one end will react.
Both ends are reacting. This alcohol will react with another acid like this. This acid will react with another alcohol like this.
But what if there was more molecules of alcohol and more molecules
They
of...
will add normally 1-to-1 ratio, so they will always have enough. And again, in industry, how they make those, I'm not quite sure, but that won't be a problem. Okay, and here is the structure of that one we just talked about. Okay, in order to simplify the structure, we know that's what? AB, 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 repeating. So we just put one AB in the parenthesis, then put an N like we did before. You guys remember that? Okay, this guy has a name. Okay, the full name, I'm pretty sure you've never heard, but the short name, the abbreviated name is called PET. Yeah, have you guys heard of PET? Anyone heard of PET? Okay, we have at least 2 PET in front of our desks. The water bottle and that Gatorade bottles are PETs. They are polyester plastics. Okay, we're using PETs every day. Those hard plastics, a lot of them are PETs. Okay, here this picture shows you the use of different PETs. Of course, those bottles, okay, there's bottles, and sometimes the balloons, the microfiber, the bubble cloth, or these bubble plastics, or some of the yarn, and even carpets, etc. They're all what? They're PETs. Especially those harder, clear plastics, especially the bottles, are PETs. They are PETs. They're around us. We use that. What are PETs? Polyesters. Okay, they're polyesters. Of course, one problem of using PETs, they're not degradable. Okay, they're not degradable. Okay, so that means you either recycle them or they will be staying on our planet for the long time. Okay, for the long time. You can see that on a bottle of somewhere. You will see a sign with a number in it. They're different recycling codes, but they're all what? PET. Good? Okay, I think I will stop here and we will continue on next Monday on more about esters. But again, guys, before I stop, please, when you study the ester, when you see an ester structure, practice now, because we'll use that a lot for the rest of the chapter. Even the short part is when I give you an ester, you need to identify the ester bond, and more importantly is to identify what? Which part is from the acid, which part is from the alcohol. Okay, I'll see you in 10-15 minutes.